Hello, my name is Jeffrey, and this is my video lab report for Physics 2211M, lab number 3. To introduce this lab, let's first analyze its purpose, its models and fundamental principles, and the main result. The purpose of this lab is to apply Newton's second law, aka the momentum principle, and demonstrate understanding of forces in curving motion, namely gravitational and centrifugal forces, and their relation to net force components and kinematics. Because this lab is all about moving objects, it's important to apply Newton's second law of motion. To predict the object's motion, we need to know the net force acting upon it, its velocity, and its position at regular intervals, or time steps. Newton's second law reveals the object's net force, as it states F net equals dp over dt equals delta p over delta t, or change in momentum over change in time. Net force can also be split into parallel and perpendicular components. The parallel component of net force is equal to the difference in magnitudes of final and initial momentum over change in time times p hat, while the perpendicular component of net force is equal to mass times velocity squared over the radius of curvature times n hat. Since the only forces at play in the lab are gravitational forces, it's also important to know the gravitational force formula. F sub g equals negative gmm over r squared times r hat. Free body diagrams, such as the example shown in the bottom right, can be used to illustrate net force. For part 2, once we know F net, we can plug it into the velocity update formula. V final equals V initial plus F net over m times delta t. Once V initial and V final are known, both values can then be used in the position update formula. R final equals R initial plus V average times delta t. As for the main results, in part 1, I found the mass of the black hole by equating the perpendicular component of net force to gravitational force on the star from the black hole. And for part 2, I found an initial speed required for the ship using kinematics and by finding the net force on the ship and on the planet. For part 1, the system is a star and the surroundings are the black hole. The initial conditions are that the black hole is at the origin and the mass of the star is 2 times 10 to the 30 kilograms. It is assumed that the net force on the star is due solely to the black hole. Delta t is 1 day or 86,400 seconds, and the relativistic constant is negligible. The selected code to the right shows how some of the conditions were programmed into the simulation. Here's the calculation loop I used for part 1. Within each iteration, I found V initial and V final, and then multiplied both by star.m to yield P final and P initial. I also found delta V, delta P, and dp dt, which is equivalent to F net by the momentum principle. I then applied the equations for the parallel and perpendicular net force components to find F net par and F net perp. By equating the perpendicular component of net force to the gravitational force exerted on the star by a black hole, I was able to algebraically determine the mass of the black hole in line 196 using the annotated calculations. From there, I used arrows to represent F net par, and F net perp, scaling them down significantly so they would fit with the display. Since the mass of the black hole would vary depending on where the planet was in its elliptical orbit, I summed all the black hole masses from each iteration and then divided by the number of iterations outside the loop. With this approach, the program found the black hole's mass to be approximately 8.51 times 10 to the 33 kilograms. It is also important to note that the net force on the star changes throughout its orbit, with both its net force and speed being greatest when it is closest to the black hole. So, what does it mean? Well, by definition, F net equals dp over dt, F net parallel equals dp over dt parallel, and F net perpendicular equals dp over dt perpendicular. Furthermore, F net parallel represents changes in speed, while F net perpendicular represents changes in direction. For example, in the screenshot of the output shown to the right, the magenta arrow indicates that that the star is increasing in speed, while a cyan arrow shows that it's turning toward the black hole. For part 2, the system of interest is a spaceship, while the surroundings are the planet and the black hole. The black hole is at the origin and has the mass determined in part 1. The ship launches in the direction of the planet's motion, and the ship has some initial speed between 0 and the speed of light. The mass and speed of the planet and the mass of the ship are defined in the portion of code shown to the right. It is also assumed that the gravitational forces between all three bodies are the only forces at play, and that the relativistic constant is once again negligible. In the calculation loop, the radius between the black hole and the planet is found, and then used to find the force of the black hole on this planet using the gravitational force formula. A similar process is used to find the radius between the ship and the planet, and then the force of the ship on the planet. Then F net on the planet is simply assigned to the sum of the force of the black hole on the planet and the force of the ship on the planet. Once again, a similar process is used to find the F net on the ship. To make the simulated planet and ship move, I applied the velocity and position update formula separately for each body. With this code, I was able to simulate different initial velocities of the ship until I found one that enabled it to come close to the black hole but avoid being sucked into it. One example of a possible initial speed is shown in the code snippet at the bottom, with the resulting orbit illustrated in the output to the right. However, if the goal was for the ship to orbit the black hole, the initial velocity would need to be a lesser x component and a greater y component. This would allow it to start tangent to an ellipse, with one of the foci being concentric to the black hole. An example of a plausible initial speed is shown in the code below, with the resulting output being displayed to the right. As a last note, there are a few possible sources of error for both parts of this lab. First, random errors from each iteration impacted the average black hole mass value calculated at the end of part 1, and slightly affected the accuracy of trajectories of the ship and planet in part 2. Additionally, not accounting for the relativistic constant also impacted results, as this would have been an appropriate scenario to apply general relativity to Newtonian gravity.